Golden Iris Production presents Introducing the Planck Constant and the Ultraviolet Catastrophe by Mark F. Dennis. Blackbody Setup. To understand the origin of the Planck constant, we begin with blackbody radiation. A blackbody is an ideal object that absorbs and emits all radiation. When radiation is trapped inside a cavity, it forms a well-defined spectrum that depends only on temperature. We describe this using spectral energy density, the energy per unit volume at a given frequency. Inside the cavity, electromagnetic waves form standing modes. The number of these modes increases with frequency, proportional to nu squared. Rayleigh-Jean's law. Classical physics assumes that each mode carries an average energy, equal to K sub B times temperature. Combining this with the number of modes gives the Rayleigh-Jean's law. It predicts that energy density increases with the square of frequency. But this leads to a serious problem. As frequency increases, the predicted energy grows without limit. Integrating over all frequencies gives infinite energy. This is known as the ultraviolet catastrophe.
Experimental failure. Experiments tell a very different story. At low frequencies, the classical prediction works well, but at high frequencies, in the ultraviolet range, the observed intensity does not increase. Instead, it drops off rapidly. Real spectra rise, reach a peak, and then decay at higher frequencies. Classical physics cannot explain this behavior. Planck's hypothesis. In 1900, Max Planck proposed a radical idea. Energy is not continuous. It is exchanged in discrete packets, or quanta. The energy of each quantum is proportional to frequency. E equals h times nu. Here, h is a new fundamental constant, now known as the Planck constant. Using this idea, Planck calculated the average energy per mode using statistical mechanics. The result introduces an exponential factor that changes everything. Planck's law. Combining quantized energy with mode density gives Planck's radiation law. At low frequencies, it reduces to the classical result. But at high frequencies, the exponential term suppresses the energy. Instead of diverging, the spectrum falls off smoothly. This completely resolves the ultraviolet catastrophe. For the first time, theory matches experiment across all frequencies.
How h was determined. Planck's constant was originally determined by fitting experimental data. By matching the theoretical curve to measured blackbody spectra, the value of h could be extracted. Over time, increasingly precise experiments refined this value. Today, the Planck constant is exact by definition. It plays a central role in the modern system of units. Physical meaning. The equation E equals h nu tells us that light comes in discrete packets, photons. This idea launched quantum theory. It explains the photoelectric effect, where light ejects electrons from a surface. It appears in Compton scattering, and in early atomic models like Bohr's. Planck's constant is now one of the most fundamental constants in physics. Wien's displacement. Planck's law also explains how the peak of the spectrum shifts. As temperature increases, the peak frequency moves higher. This means hotter objects emit more high-frequency light. That's why hot objects glow blue, while cooler ones appear red. This relationship is known as Wien's displacement law.
Summary. Classical physics led to the Rayleigh-Jean's law and the ultraviolet catastrophe. Planck resolved this by introducing quantized energy. His formula matches experimental results across all frequencies, and the constant h became a cornerstone of quantum physics. At a deeper level, Planck treated each mode as a quantum harmonic oscillator. Using a partition function, he calculated the average energy per mode. This leads directly to the Planck distribution. Multiplying by the number of modes gives the full energy spectrum. To be continued.